Great, thank you. Cool, yeah. So I'm Dan, I'm a grad student in the AMP lab, the RISE lab now. And yeah, I work with Joey Gonzalez, Jan Stojka, Mike Franklin. And I'm going to talk about a system that has very little to do with Spark, except that the success of this system is sort of predicated on the success of these of systems like Spark in terms of training large-scale machine learning models. So before I jump in, I want to sort of set the stage with a little bit of motivation. So this is a slide or a process that probably many people in this room are familiar with. When we talk about machine learning, a lot of times this is sort of what we're talking about. Taking some often large data set and training it with a system like Spark. I have TensorFlow up there because I've given this talk at Google before. And the end result is often some large, potentially complex, and these days fairly accurate model. And when we talk about this type of thing, we're talking about timescales of sort of minutes to days. We're talking about systems that are generally run offline in large analytics clusters, are optimized for batch throughput. And this type of system is pretty well studied these days. This was a heavy focus of the AMP lab with systems like Spark and all of the machine learning work that was built on top of Spark. But what I'm going to talk about today is sort of all the other things that go into actually using machine learning in a practical application. So clearly, learning is important. But what happens after we train the model? If you're an academic, maybe that ends with a curve in a paper, some state-of-the-art result. But for many people, you want to use that model to actually do inference. You want to take in queries and use that model to make real-time decisions. And here, we're now suddenly talking about timescales on the order of milliseconds. We need systems that are online and latency optimized rather than throughput optimized. And this type of thing is much less studied. And then finally, our predictions don't just sort of disappear into the ether. They go and they hopefully influence sort of real things happening. And we can observe the results of making these decisions and gather feedback and use that to actually further refine our machine learning models and improve our accuracy. And often with feedback, we're once again talking about timescales of sort of hours to maybe weeks or months, sort of timescales on the order of the next time I decide to rerun my Spark job to retrain my model, whether that's hourly or nightly or maybe never. And often the way to do this is some combination of logging and message queues and Kafka, and then sending that to Spark Submit when you have enough new training data collected. It's sort of this ad hoc process. So in the RISE lab, one of the things that we've been thinking a lot about is how do we build on the work of the AMP lab, all this great work on training, doing large-scale training, and think more about this inference process and how to do it responsively with low latency for a wide variety of applications, and how to better incorporate feedback beyond just using it to retrain a model. How can we actually get real-time adaptivity and start to use this new information that we have about the world more quickly? So if you're going to build a machine learning application today, it might look something like this. You take your data set, you train a model using your favorite training system. And then often what's done is you actually just continue that batch job and use it to score some things that you want to score. Maybe you generate your movie recommendations offline once you've created once you've trained your Spark model. And then when you want to serve these things, your query comes in and you just look up that pre-rendered decision, that pre-materialized prediction in some key value store and render the decision. And we can easily do that in 20 milliseconds. You can do that in less than a millisecond. But there's some problems with this approach. Probably the biggest one is that it requires you have the full set of queries that you need to make predictions about ahead of time. And this is becoming less and less true. This is certainly true with certain types of content recommendation applications, but it's not true for fraud. It's not true for personal assistants like Siri, anything you want to do with speech or images or things like this. Because you need a small and bounded input domain. even if you can generate the full set of queries you might need ahead of time, often you end up doing a lot of wasted computation and wasting a lot of space because you render sort of all of these things ahead of time whether or not you need them. And you can incorporate feedback, and these things are costly to update, and you're crossing from sort of your analytics cluster into your key value store, and there's a lot of ways for sort of bugs to creep into this. And I think what we're learning in 2016 and 2017 is that it's really, really easy for machine learning applications to have lots of very subtle bugs that are very hard to detect with traditional programming language tools and software development tools, but that can really destroy your accuracy. Or have other more sort of pernicious effects like what we've seen with Facebook and news in the last year, for example. So really what we'd like to do is not do this pre-scoring, but actually inject our machine learning models into our serving systems and actually render our predictions with models in real time. And people are starting to do this. I'm certainly not the first one to suggest this. There are companies who have been doing this for a decade or more, and even with complex models. But there's some problems with this today. Let's say I start out with a fraud detection application, and I use a Spark model. Maybe I train some really big linear model in Spark, and that works pretty well. But as anyone who's worked with machine learning in practice knows, machine learning is not a one-stop process. It's iterative. You're constantly refining your models, experimenting with new features. Maybe I have some cool new features that I'm using deep learning with. So now I want to take my application that was previously integrated with a Spark model and integrate it with TensorFlow. That's a whole bunch of new code I need to write. Or maybe I want to set up another application that's not fraud detection, that's content recommendation. And maybe I want to use TensorFlow for that and fraud detection, but Spark just for fraud detection. And of course, this goes on and on. We have lots of different applications with lots of different methodologies behind them. And we have lots of different machine learning frameworks. I know that this is Spark Summit, but there are lots of different ways of training machine learning models. And even within Spark, there's lots of different ways of training machine learning models. People are using Spark to train TensorFlow models. And so we have lots of applications and lots of models, and we have this many-to-many dependency that leads to these brittle, ad hoc deployments and really raises the barrier to entry for creating machine learning applications and for iterating in them the way that data scientists want to. So with this project, we asked the question, can we decouple models and applications? I'm a systems guy. Can we stick a system in between these two things that seem like they should be fairly independent and let these two things sort of and gain the true benefits of having independence where dependencies are not needed? So we're calling this system that sits in between these applications and models a prediction serving system. And I want to walk through what I think some of the requirements are for this type of system. And then I'm going to, of course, talk about how Clipper satisfies these requirements. So this type of system, its primary goal is to decouple applications from models and allow them to evolve independently from each other while still providing the full functionality needed to serve applications and to deploy models. So from the perspective of the front-end developer, the guy building the application, and his DevOps team, the people responsible for making sure that these things run in production, they should be able to focus on building reliable, low-latency applications. That means that this prediction serving system needs to provide stable, performant APIs that can meet service-level agreements, provide the right knobs to scale to different types of workloads and application demands, and let them remain oblivious to the implementations of these underlying models. The guy who's just asking, is this fraud or not, doesn't really care how that decision is being made as long as it's accurate. And then from the perspective of the data scientist, they should be able to focus on making accurate predictions. That means that we need to support lots of models and lots of frameworks simultaneously. We don't want to tie the hands of data scientists. We want them to leverage the full rich ecosystem of tools that are being developed and talked about at places like Spark Summit and Hadoop and in academic conferences and at NIPS and being developed by large enterprise companies. We should simplify the deployment process. We should allow them to do online experimentation. We should allow them to do things like use multi-arm bandits and all these sort of cutting-edge machine learning techniques that are actually really promising and have huge efficiency wins over traditional things like A/B testing. And we should let them be as oblivious as possible to system performance and workload demands. Now, if you're trying to deploy a model that takes 200 milliseconds to render a prediction, and your application has a 20 millisecond SLA, of course, that won't work. But you shouldn't need to know that suddenly my throughput doubled and the DevOps guy needed to spin up another machine. That shouldn't involve the data scientist at all. So what does this look like in Clipper? Well, Clipper, if you're a front-end developer, looks like another microservice. We expose a very simple REST API. You can request predictions, and you can provide feedback. And then there's a management API as well, so that you can do things like create new applications and have Clipper running in a multi-tenancy environment, deploy new models, replicate models to increase your throughput, inspect the instance, look at different system performance metrics, and so on and so on. And then from the data scientist perspective, they don't really have to think about the fact that Clipper is a serving system running in prediction. Basically, they implement this model API. This is how they plug their models into Clipper. It's this very simple API. They say how to load their model. So, if you've trained a model in scikit-learn and persisted it with the joblib pickling library, you say, your init method is, unpickle the serialized model. If it's Spark, you read the Parquet file, so on. And then you say how to make a prediction. Any data scientist who's training a model knows how to make predictions because they're constantly doing that as part of the training and development process. And that's all they have to do. They plug this model, they implement this model container API. And because it's such a simple API, we can implement it in many languages. So if you're using a framework written in Python, implement it in Python. If you're using something written in Java, implement it in Java, and so on. We take this model container implementation, package it up in a Docker container that has an embedded RPC client that Clipper knows how to speak to, and then communicate with Clipper over RPC. This means that we can have I apologize for the fonts. We had to do a last-minute computer switch. I think that's supposed to be cafe. I'm fairly sure. But you can deploy, multiple models in the same Clipper instance, even trained in different frameworks, written in different programming languages. And the data scientist doesn't really have to know about any of this. They just have to implement that simple model container API. And then when you stick it all together, you get this system that's interposed between your applications and your models, and is this prediction serving system that we think meets the requirements that I outlined in my previous slide. So what are some of the challenges we needed to solve in order to actually implement Clipper? I've talked about what Clipper looks like from the outside. What does it look like from the inside? Well, one of the big challenges is that there's sort of heterogeneity throughout the system. We have different types of models, different software. They have different types of physical resource requirements. You really want your TensorFlow model running on a GPU, but you probably don't need your scikit-learn model running on a GPU. It probably doesn't even support that. And we also have different application performance requirements. We have different workloads, different burstiness, and also different latencies that we need. Some applications that are really critically user-facing, you might need a prediction in 2 milliseconds or 5 or 10 milliseconds, whereas others, 50 milliseconds or 500 milliseconds or even a second might be OK. We should be able to support all of that. We have scheduling questions. As it turns out, and I'll get into this briefly a little bit later in the talk, how you send these predictions to these models can have a dramatic impact on the efficiency of your deployment and the amount of physical resources you need to meet these workload demands. Throughout this thing, there's sort of latency and accuracy trade-offs. Is it better to be slow and accurate or fast and inaccurate? And these questions vary for different applications and different models. And then there's also questions about what's the marginal utility of allocating additional physical resources. From my conversations with people who have done this stuff in production, the cost per prediction is sort of their critical metric in making machine learning useful. And then finally, how do we use that feedback, that red loop that I showed that completes this loop, to improve accuracy in real time? So I'm going to briefly go through how Clipper addresses these challenges. The work I'm going to describe in the next 6 or 8 slides is work that we did for an NSDI paper that's going to be published this year. So this is sort of a little bit more of the research work. Some of this is in the Clipper open source system that we're developing, and some of it's on the roadmap. But internally, Clipper can be divided into 2 layers. We have this model abstraction layer, and this is what's responsible for making that common interface, that model container implementation, actually performant and work well in your production setting. Bounding latency, maximizing throughput, maximizing physical resource utilization. And then we have this model selection layer. And this is the thing that uses that feedback, implements bandit methods, ensembles, online learning, can do some personalization to utilize that feedback and react to this new information that we're getting in real time to maximize your accuracy. In the model selection layer, we actually do some learning in the serving system. Now, that's not going to be retraining your Spark model, your TensorFlow model, but I'll get into some of the types of learning that are useful to do in this really low latency setting. So then internally, your model selection layer is represented by what we call a selection policy. And this is just the implementation of the logic that takes in this feedback and makes decisions about what models to query and how to weight predictions and things like that. And then in the model abstraction layer, we have caching. We have some batching that we do to maximize our throughput. So I want to briefly talk about each of these layers. Excuse me, I'm getting over a cold. So in the model abstraction layer, we start with these model containers that communicate with Clipper over RPC. Now, this common interface, as I mentioned, dramatically simplifies deployment, and it also eliminates a common class of bugs that happen when you have to re-implement your model from the training software to the production software and duplicate that code. So to avoid all of that stuff, we let people evaluate models using their original code and their systems, and I actually feel really strongly that this is really the right way to do this. That doesn't mean that we shouldn't be putting fast paths for prediction and evaluation into our machine learning frameworks, but we should eliminate that code duplication to avoid these classes of these bugs and all these hidden assumptions. And then as a result of this, they're running in Docker containers, so these models are run in separate processes. This provides resource isolation. It allows us to really easily scale these things out. If we need more throughput from a given model, just create another Docker container instance. Now, we do run into a problem here with using the original code, and that's that a lot of these frameworks are optimized for batch processing, not for latency. And a lot of times, these assumptions about high throughput, but potentially high latency implementations percolate throughout the whole system implementation. So one of the things that we found that's really useful for dealing with this is using batching to evaluate our predictions with sort of micro batches. So why does batching help? I'm going to list a bunch of really unsurprising reasons. One is that often your queries actually arrive in batches. A single sort of user click might generate actually a whole set of prediction queries that need to be evaluated. A lot of these models are built to use hardware acceleration, things like GPUs or BLOS or vectorized instructions. And then it also helps amortize some of these system overheads that are inherent in using an RPC system. Now, we're able to pretty much amortize those away, but that is an overhead that we needed to deal with from an engineering perspective. But the problem here is that how you do the batching is actually really, really context dependent. It depends not just on your hardware configuration, how big is your GPU memory, not just on the model and framework that you're using, but also on the system load at this point in time. So we found that one thing that's really effective is basically be as slow as allowed. When you create an application in Clipper, you specify a latency objective, and we basically treat early returns before that latency objective as there sort of being no win there. So we can be as slow as allowed as long as we meet that objective. So if you need predictions in 10 milliseconds, set the objective to be 10 milliseconds. We probably won't return predictions in 5 milliseconds, but we'll make damn sure that we return predictions in 10 milliseconds. And by doing this, it allows us to increase the batch size until the latency objective is exceeded. So we have some queuing logic to figure out how big we can make batches without exceeding our latency objective. And then if we do, as we're sort of exploring the right batch size to use, if we exceed it, we'd use a multiplicative decrease like we do in TCP. And this actually works really well. We tried some fancier stuff. We tried learning sort of a quantile regression to estimate these curves. And that works sort of just as well, but no better. But we're exploring some different ways of doing this adaptive batching and learning the right batch sizes so that we can adapt to different latency objectives even within the same model, for example. So I'm going to show you one result slide just because it was sort of really surprising to us how effective batching was. Turns out if you don't do this, you get really, really poor throughput, all these low lines on the top graph. But if you increase the latency objective up to the 20 millisecond objective that we set here, and we can talk about why the kernel SVM looks terrible in this plot offline, you get really big wins. We got wins up to 25x throughput improvement just from this very simple thing. So now I want to briefly talk about how we use feedback and what types of learning we do in the selection layer, and then I'm going to wrap up. So as I mentioned, your predictions don't disappear into the ether. You can observe the results of them and gather feedback. Sometimes this feedback is explicit, like, did this user click on this image? And sometimes it's a more implicit reward of this user spent this much time on this page. So there's lots of different types of feedback that we can get. And in Clipper, we short circuit this long feedback loop. We don't try and eliminate it, because that's still a very useful thing to do. But we include this fast feedback loop as well. And bring learning, and with that feedback loop, we bring learning into the serving tier. So what are the types of useful learning that we can actually do with minimal compute resources and with sort of minimal training data, and without overloading our production serving system? Well, we can do things like dynamically learn the weights when using a mixture of experts. Or we can select the best model for each user using a multi-arm bandit algorithm. It might be that some users are better modeled with a more user-centric model, and others are better modeled by a more time-centric model, for example. Or we could even use the selection policy to learn that it's me browsing my Amazon account right now, not my brother or my girlfriend or my mom. Not that my mom browses my Amazon account. Say Netflix. There we go. We can also use we can use ensembles. Often, as you're iteratively refining your machine learning framework, you have multiple models that may work well for a given application, and you can use these to estimate your prediction confidence. This is particularly useful for things where you want to know, where you want to take a default action if your model isn't confident enough in sort of edge cases. And what we're explicitly not trying to do is try and retrain these models. We're not going to try and train your Spark model in Clipper. We have a great system to do that. It's called Spark. It's why you guys are all here. So that's sort of the state of Clipper research today. But we are building an open source system, hence the fight around Rust versus C++. It's already open source on GitHub. And you can kick the tires. We have a tutorial that I got merged in about 45 minutes ago. It's kind of cool. It uses CIFAR. It sort of walks you through all these things that I talked about: starting Clipper, creating an application, deploying models, running, querying the application. And it uses the CIFAR data set, and you end up training and deploying a scikit-learn logistic regression model, and then a TensorFlow convolutional neural network. Where I want to explicitly say that we haven't provided a release yet. So it's open source, check it out. It's under active development, but we're hard at work on an alpha release, something that's actually, we think constitutes a complete minimum viable system that you might want to try and deploy in, if not production, start evaluating for that. So that release is going to be focused on providing a reliable and performance system, because I think that's really the building block here, is if your DevOps guys won't deploy this in your production serving cluster, sort of, we've already lost. And we're going to start simple and provide a reliable and performant system for serving single model applications, not try and get too fancy with the feedback quite yet. We're going to have first-class support for scikit-learn and Spark models, and we're also going to allow you to serve arbitrary Python functions, because actually often the best way to prototype a machine learning model is to not use machine learning. And we're coordinating our initial set of features with our RiseLab industry sponsors and collaborators. And then after the alpha release, this spring and summer, our next priorities are actually fully supporting this entire model lifecycle, supporting selection policies and multi-model applications, providing model performance monitoring and anomaly detection and correction so that we can detect when someone changed feet to inches and now your accuracy is terrible, which are things that happen all the time. And then we're also hard at work on a new task scheduler design to really take full advantage of this heterogeneity that I mentioned before. So check us out on GitHub. I, of course, was tweaking my slides right before, and I forgot to put the URL, so I feel like an idiot. But it's if you search Clipper, or it's on the UCB Rise Clipper repo, it should be very easy to find. Go to the RiseLab website, check out our new lab. And then we also have a paper that's going to be an NSDI, and that's already up on archive. And if you want to know more, send me an email, check out our repo, file a GitHub issue, and please, I want your feedback. Thank you very much, and I think I have a couple minutes to take questions.
So we have about 90 seconds here for questions. Your hand went up first in the back, and then we'll come up here.
Any plan to roll this into Spark?
No, because it's an independent system. We have plans to make Spark a first-class citizen, but there is no part of Clipper that runs on the same hardware or with the same system as Spark. So sort of the process is you have your Spark cluster running in your analytics cluster, and once your Spark model is deployed, you deploy that to Clipper.
So the question I had is over here.
Oh, thank you.
Have you tried deploying a Spark model into Clipper? Because we do have some version of this kind of serving system, and one of the problems we've encountered with the Spark models, specifically in the 2.0 release in the pipeline framework, is that, as you said, the models that Spark provide were optimized to create predictions for entire data sets, not for specific rows. Are you planning to negotiate with the Spark community so that we can also get kind of row by row level predictions? We've worked around a little bit that, but maybe there's a better solution that involves Spark changes as well.
Yeah, that's a great question. Two really quick answers. One, we've faced the same thing, and we basically can't do low latency predictions with the pipelines API because it takes there's about 20 milliseconds of overhead just to create the RDD, or the data frame. So there is an open Jira issue that isn't seeing a lot of activity. There's a project called MLeap, which I'm aware of, and I'm not super familiar with it, but they're definitely tackling that as well. And my understanding is that there's some collaboration with Spark and the MLeap project. And as we're preparing for this release, that's going to be something that we're going to be thinking about more, because it is a huge limitation, and I really think that that's something that the Spark committee is going to need to address sooner rather than later.
All right, we're out of time here, but you can talk to Dan in the back. Meanwhile, Dan, thank you very much for coming. Really appreciate it. And